Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to solve the question mirror delete. This prompt states you're given the head node of a singly linked list, and you want to remove an item within this linked list. Instead of given the index of the item we want to delete from the beginning, as we typically are, you're actually given the index from the tail, so it's the index going backwards. We will have standard linked list nodes, where we have a data property and a next pointer that points to the following item in the list. Then we construct a linked list as this, and we see that the k, or the index that we want to delete, starts from the tail. So from the tail going backwards, it's 0, 1, 2, 3, 4, 5. Then we call our mirror delete function, we pass in the head, and the k index of the item we want to delete. In this case, it corresponds to 6, which is 0, 1, 2 items back from the tail. This question also has some strict constraints. We can only iterate through our linked list in one pass, so we can't go through it multiple times to find the item that we want to delete. We also don't know the size of the linked list. It can be arbitrarily large. The k value we pass in will always be greater than or equal to 0, and k equals 0 starts at the tail node going backwards. If there is no node that can be removed, we simply return the same linked list without making any modifications. So the way we normally delete a linked list node is we start from the beginning or the head node, and we're given an index. Then we iterate that many items into our linked list, and set the preceding node's next pointer to the item after the one we want to delete. So the node we want to delete is just skipped over in the list and therefore removed. Then our programming language just clears that item from memory. So our mirror delete is going to be very similar. We're going to find the item before the one we want to delete, and then set its next pointer to the item after the one we want to delete. So if we want to delete the k equals 2 node, we have the tail k equals 0, 1, 2, but then to delete the item, we actually need to get to k plus 1, which is 3 in this case, and then we set this item's next pointer to the one after it. So to solve this, if we knew the length of our linked list, we could simply take this linked, subtract k, and find where we need to delete the node and iterate that many spots in. But we don't know the length, and we also can't calculate it. We can only go through our linked list in one pass, so once we got to the end to find the length, we've already used our pass and then can no longer start from the beginning for a second time. So if we can't find our k spot based on the length, the only way to accomplish this is then to find the tail and also the k plus 1 spot at the same time. So there are two landmarks we want to track. If we can find the tail node, we can also know the item we want to delete at the exact same time. Or more specifically, we want to be one item past it from the tail at the k plus 1 spot, so we can delete it. So how can we find the tail node and the k plus 1 spot item in one pass without breaking our constraints? This question never says anything about how we do our one pass, so we can use a second pointer, or implement something called the runner technique. There are a few ways to implement the runner technique. In our case, we're just going to start a lead pointer, k plus 1 spots, into the linked list. Then, once we reach this point, we'll start our follow pointer and iterate both of them forward at the same time until our lead pointer reaches the tail. Once the lead pointer is on the tail, our follow pointer should be k plus 1 spots behind the item we want to delete. Then, we simply set its next pointer to the item after it to delete the k item and return the head. So the logic is actually pretty straightforward. With 2 pointers, we can find our 2 important landmarks, which is the tail, and then by knowing the tail, we know the k plus 1. But this also introduces some edge cases, so we're going to walk through it and then handle those edge cases at the end. And now, let's walk through a full example. Let's say we want to delete the k equals 2 node, or this node that corresponds to the value 11. It is 0, 1, 2 spots back from the tail. We are first going to start our lead pointer. To use the runner technique, we're going to iterate this item 0 to k spots into the list. Then once we get here, 0 to k, it's k plus 1 total items since we started at 0. And then when we start our follow pointer, it's going to be k plus 1 spots behind. So lead is technically at 0, 0, 1, 2, 3 spots for the follow pointer. So now we have both being tracked. We move our lead pointer and our follow pointer forward at the exact same time by 1 spot. They iterate simultaneously, and then once our lead pointer reaches the end, or the tail node, our follow pointer is k plus 1 spots behind. So 0, 1, 2, k plus 1 is 3. And then, to delete the item at k equals 2, we set our follow pointer's next pointer to the item after the one we want to delete. So follow.next equals follow.next.next. This means no items in our linked list are pointing to the one we wanted to delete, so it's no longer referenced and cleared from memory. Now this item has been removed from the linked list, and we can return the head and we're finished. And that's it. That's our entire logic. But now we also need to think through these edge cases. So let's look. There are a total of 4 possible cases that we'll need to handle. Where k equals 0, or is the tail node. Where k is within our linked list, or are similar to the case we just saw. Where k equals the linked list length minus 1, or the head node. Or where k is larger than the linked list, and we can't delete any items. So let's walk through these one by one. Our case 1, where k equals 0, this means we want to delete the tail node. So when we start our lead pointer for the runner technique, we only move it to the first spot. Then when we iterate through, it's going to land on the tail. Then our follow pointer should be 1 spot behind it, and we set its next pointer to null, which removes the tail node. When we want to delete an item within the middle of the linked list, we just move our lead pointer forward. Then we move the follow and the lead at the same time until the lead reaches the tail, and we can delete the item at the k spot. The most tricky edge case is probably deleting the head node, where k is the linked list length minus 1. Since we can't technically land in front of the head spot, we just need to return the item after the head node to delete it from the list. So what's going to happen is we're going to iterate our lead pointer all the way forward, and it's going to land directly on null. Then if it is on null, we know we want to delete the head node, so what we do is return head.next, and then the second item in the list is just our new head node. By returning a new head, it will be recognized as deleted, and our list will just start at a new location. The final case is where k is greater than the length of our linked list. If this happens, then we simply just return the exact same linked list without any modifications. And that's our logic. So we're using 2 pointers, doing something called the runner technique, where we have a lead pointer and a follow pointer. We iterate the lead pointer head k plus 1 spots, which will mean the follow pointer is k plus 1 behind. And then we iterate our lead pointer until it reaches the tail node, which means our follow pointer is at the k plus 1 spot. We set the follow node's next pointer to next.next, which just means it skips the k item and removes it from the list, and this deletes the node that we're told to remove. So our big O of this question is O of n time and O of 1 constant space. We must iterate through all the items, going from the head all the way to the tail using our lead pointer, and we only do this in one pass. We use the runner technique and introduce a second pointer, so we have a lead pointer and a follow pointer, and each of these are constant space, and we add no new data structures. And now we're ready to implement our solution function mirror delete. Our function takes the head node of the linked list, and the value k, or the item that is k spots back from the tail that we want to delete. We're using the runner technique, so we initialize a follow and lead pointer that both start at the head. Our lead pointer is going to be moved ahead k plus 1 spots. So we just say lead equals lead.next, which moves it forward 1 spot each time. We also don't know if k will be larger than our linked list, And if it is, this is one of our edge cases. We need to check if lead reaches null before iterating it forward, and this indicates that our k value is larger than our linked list, so this is one of our edge cases. If k is larger, then we get past the end of the list. We know we won't delete any items, so we just return head, which means no modifications have been made. We also need to handle our second edge case. So if the last item lead lands on is null, so it lands one spot past the tail, that means this for loop will have finished, and lead is exactly null. In this case, we know we wanted to delete the head node, which is the length of the linked list minus 1. So to delete the head node, we just return head.next, which gives us a new head. So this is our second edge case. If neither of these edge cases return, then that just means we're somewhere within the linked list with the lead pointer. So now we want to iterate forward both the lead and the follow simultaneously by one spot each. Then, once the lead pointer reaches the tail node, we know our follow pointer is k plus 1 spots back. Then we just set the follow pointer's next value to the follow.next.next, which will delete the k item. And then we simply return our head. We've handled when k is larger than the linked list, when we want to delete the head node, or when we want to delete any item within the linked list that is between the head and the tail. But this also handles deleting the tail, because our lead pointer would have just iterated one spot into the list, and the follow pointer would just be one spot back to delete the tail. So we've handled all 4 of our cases. Let's run our code. So we've successfully mirror deleted a node in this list. This is a great linked list interview question to practice. It makes you think through iterating through a linked list and handling edge cases, and also implementing the runner technique, which is used in many other linked list questions. Thanks everyone, and I'll see you in the next lesson.